Hi, dear T and Professor. This is Yan. I'm here to present my final project. So I'll start with the Jupyter Notebook first. So we need to install the packages and download the data from Cargo. I have done that. So I delete that information because it has been downloaded and unzip it. So we need to call the data from my folder, both the training and validation. So first one is the convolutional neural network. And we can see that 52,000 of data is belong to the training and 1,500 belong to the testing. And because there is an imbalance of the classes, so I'm using data augmentation for the convolutional neural network to avoid overfitting and for better training purposes. I plot some samples here. So for the models, I will describe more in the report session. So we can add different layers, do max pooling, do batch normalization. You can also change the filter size and also dropout rate, the regularization, and also use different optimizer and different learning rate. And we need to compile it before run it. And this is a summarization. And I have tested different architectures. And yeah, this is a training process. We need to use the augmented training data set for training and use the normalized validation data for validate. This is all the training process, and then we can also plot the accuracy and the loss and also the confusion matrix. And we can see that it does not perform that good for this model as the predicted spike, however, it is truck, so it is wrong. And then to plot some pictures, like for this one, it is car, but the true cost is spike, but it's predicted car. So this is misclassification example. And then here is like what we do for the model 1 is correct, but model 5 is got it wrong. It is bike, but model 5 predict as a person. So this is all the code for convolutional neural network. And the next one is for the VGD, so the pre-trained VGD16. And there are like more than 15 layers, which is more complicated and have more information. Similarly, we need to import the train data set and the validation data set. And then we need to download the VGG base. However, we can freeze the blocks and or train some of the blocks. So we can, if we don't want it to be trainable, just make a trainable equal false, and for other layers, make the trainable equals true, and then add different dense layers. The dense layers, and we can also change the different nodes in the dense layers. So the other are all the same with convolutional neural network. And that's it. And then we can freeze different blocks, freeze different layers. And same training process, same the prediction. We can get F1 score, we can get the AUC, and also we can calculate the confusion matrix. And finally, which is the autoencoder plus the dense layers. The same as previously, doing the import, the tree, and the validation. And the input, we have the input shape. And the first line is the encoder. We are doing the encoder here. And this is the latent space. And then we are going to decoder it back to the original format here. And then for the autoencoder, we need to train it first to minimize the loss. And after that, we are doing the classification here with the dense layer. Here is a classifier. And this is a full model, which is a combination of autoencoder and the class and the dense layers. Yeah, here it is. And similarly, we can change the number of layers in the autoencoder and also the dense layer and different filter size and everything. And here's a training process for the autoencoder, and we are extracting the features and train the and for the classifier. And similarly, I have done a lot of testing here. And this is when one is correct and another is incorrect, which will be talked about more in the report. So this is done for the code for the IR for the RGB here. Sorry, for the RGB here, everything will be the same except the training data set and our validation data set. The process for training different models are the same as IR, so I won't talk about more about it. I will go to the report. So for the report here, so this is a general introduction here. So these architectures including a CNN, a pre-trained VGG, and autoencoder combined with dense network. And for each architectures, different parameters will be tested, including the number of layers, localization techniques, number of nodes to optimize the performance, and the evaluation will use accuracy, confusion matrix, area under curve, and F1 scores to provide more comprehensive of each mode capability. And also discuss like why this model doesn't perform quite well as the other one. And also there are examples can find the appendix. So in the data description, so from table 1, we can see that like most of the images are car, which is expected because like it is in balance. And but there are very few number of trucks. Like for here at RGB validation, there are only 36, which is quite small. So we need to use the data augmentation. So for CNN, we'll test different number of convolutional 2D layers, different dense layers, the number of pooling layers, the size of the number of filters, and the size of filters here. And we'll test different localization and dropout rate and everything here. So so why because CNN doesn't perform that good is might because they priority different visual features like different layers. Some architectures emphasize on local thermal signatures like bright spot or contiguous area, where others better integrate contextual information. For example, the bicycle wheels appear as a human figure, bright bus surface mistaken for light sources, or the rectangle shape of bus confused with a car. So this is for the CN, and these are the plots and the confusion matrix. So for the VGG, I also test like phrase different blocks or train different blocks, the number of dense layers. And L2 localization has been tested before, so we are using the same as previously. And there are different parameters and their accuracy, AUC, and the F1 scores. And these are the plots. We can see that it performed relatively better than the So why it is different for different models? It might be because the classification different, like VGG layers architecture processes thermal features differently depending on their train weight. So for example, when white lights are misclassified as signed, the model focuses more on the defined edges and consistent internal temperature patterns that characterize signs. For AE here, for autoencoder here, I also tested different autoencoder layers, like 2 encoder, 2 decoder, 3 encoder, or 3 decoder, the number of filters, filter size, and the latent space dimensions, and also the number of dense layers here, and the number of nodes. and everything here. So if it is classified correctly by one but misclassified by another, this might be the because the autoencoder will compress the thermal using autoencoder representation priority, heat intensity pattern over spatial relationship, causing confusion. For example, between motor and science, motor produce a concentrated heat spot, while science shows more uniform rectangular thermal signatures. Yet both create a similar pattern after the compression because we are reduce the dimension to like 1D dimension. And similar everything will be similar for RGBs. However, there are one differences because unlike the thermal images where heat signature dominates, RGB rely on color contrast and shape recommendation, and this hold for all of the images. And the testing process will be similar with IR data, so different layers, different disk layers, and different size of filters and number of filters. And for the VGG, same like VGG deep layer detects similar rectangle vehicle structures while missing scale differences, and this is possible. And also, for example, the bright light patterns triggers a specific filter activation that causes motor classification, and it reflects VGG fixed feature hierarchy where early layers detect simple edges, while deeper layers can detect complex object representations. And these are the plots, and also for AE and dense network, testing the same thing at the IR, and similar reasons here, like it will reduce the complex visual information into a limited feature space before reconstructing it. For example, the straight line with text on reflective background are complex in a way that allows the fine texture details, but preserve the high contrast and brightness pattern, make them like resemble light source after reconstruction. And we did everything the same here. So for discussion, VGD performed the best with average accuracy, validation accuracy more than 95%. And this is might be because their VGG16, like the pre-trained on ImageNet, has a strong foundation of general visual features. So, and it's like the 16 layers. So in both the hierarchical representation where early layers capture fundamental features while deeper layers learn abstract concepts. So I have talked a lot the limitations of both of them, CN and AE previously. So CN and the layers are detecting different things, while autoencoder will reduce the dimension of the images, so lose a lot of information. And also back to the best VGG pre-trained models. After the experiment, it is found that the model doesn't have to be fully trained. We can just freeze the first 4 blocks and then only train the last. This will save a lot of time and also preventing the overfitting and will shorten the training time, provide more reasonable result, and more computational efficient. And that's it. And here are all the images. And thank you for listening, and thank you for this lecture.